So imagine you're a person and your job is to check the quality of a certain product. But how do you really do that? Do you just check one sample at a time? Or do you check one sample out of many in a batch? Or do you check one batch out of a group of batches? Do you check the entire thing one by one? All of this can get really confusing really fast, but that's exactly what the job of a quality control inspector is. But did you know that automation has come a long way and quality control can be automated in a lot of ways? So in automated quality control, you're going to have some sort of feed through, like a conveyor belt, and something to check the sample, like a camera, and something to reject the sample if it's bad. In this case, it's just a punching glove. So imagine a good sample comes through, the camera checks it, and it's on its way. It doesn't have to be rejected. Now, if a bad sample comes in, it'll hopefully be able to pick up the error or the defect and throw it away in the trash. This is the basic concept behind automated quality control. Alright, so why do we need quality control? Recalls, lawsuits, why indeed? Well, what kind of quality control inspection is there? Well, there's aesthetic, which is what we are going to be going through, and then there's shape, which is like a 3D scan to make sure it's the right shape. And there's chemical, which is usually like a sensor. And rigorous testing is moreover like, shaking a product to make sure it doesn't break, and usually it's done by visual inspection. So the things that I'm going to use for data acquisition and processing is basically just a camera and Python scripting. So honestly, this self-made rig would be, just lights and a camera, and hopefully the samples would be in the same spot, but it just didn't work out because USB cameras, they couldn't really zoom in or out or adjust properly. So what I did is I just went to Staples and then I used one of their scanning machines, and they were nice enough to let me have a free black USB to put it on. But make sure you keep track of that USB because it's kind of hard to keep track of it if you lose it, Took me a while to find it and all that. So what we have here is basically the samples that we're going to use to try and face this challenge. And that involves 18 samples used to optimize the algorithm. There's defects, which are the same card but they have small mistakes with them to compare. And errors, which are cards that are completely different altogether. And one sample to compare for control purposes. Alright, so right now I'm going to go through the basic program, which shows the comparison between each algorithm and different color settings for the images, such as RGB, gray, and HSV, which is hue saturation value. The three different algorithms that I came up with are whole pixel difference, particular pixel difference, and there's another one. I don't know, pixel amount comparison. And let's go through and explain. These functions are basically, after I cleaned up the code, I made them into functions and it allows it to be cleaned up, and later on I can use the functions more easily so I can do different things with them. And so this is where the program really starts, is right here, where it opens the images and puts them into variables, and it kind of makes it an image object, which means you can access different parameters of each image and basically play around with it a little bit. So after that, the first thing we did was, for the pixel amount comparison, we made pixel arrays 1 and 2. And they're stacked as 0 to 256, and this is supposed to represent RGB, or first, second, and third coordinate. And then we have the HSV pixel array. Actually does this for all three picture settings. And for gpixel, it actually only has 2 for whatever reason, but it's basically a gray picture. And let's see. Then we have the HSV picture array. And this is where it kind of gets kind of weird. And this is 982 by 719, which is actually the picture size that we're checking at. Or the other ones are just checking the amount of a certain pixel. So let's look at this. RGB gray pixel amount processing, and it does this for each picture, and it actually puts it into those arrays. And so let's go look at what that looks like. RGB pixel amount processing. So it says go through the picture, and at the coordinates set by the loop right here, it's going to say get the pixel out of that image object, and then it's going to add it to whatever array position it has. And this is really just amount of a certain kind of pixel, really. And okay, so that's pretty much it. And you have other stuff like the gray and HSV. So for gray, there's only 2. And that's reflected right here, where there's only 2 variables being used instead of 3 for the access of an array. So in HSV, it looks a little bit different. I added this because it'll actually turn it into red if you don't. It considers white and black as red if you max out the hue value, or actually it's basically if you nullify the S and the V value, because I just want to look at the color, honestly. So then you have color sys. This is a color sys function. So I'm not really going to get into it here, but it basically just turns RGB to HSV and assign it here. And then we actually use the bits of that right here, and we nullify the value right here. It turns it into RGB1. Then RGB2 is basically the points of that turned into integers, because it can be a decimal. I don't want that. And then it does the same thing. Array name, blah, blah, blah. Adds it to a particular pixel. And so then let's go down and check what the next one looks like. So now we have to look at this chunk of code. And so in this chunk we have whole particular pixel checking, and it has it for all 3 settings. So there's 6 things total. And what we're looking at here is, let's go through it. But gray only has 2 points to check, and RGB and HSV has 3 total. So let's check this whole pixel difference 3 by image. And this is whole pixel difference. For HSV, it does it by array because we get the image and then I realized that the image isn't already put into an array. So I had to make this function. So let's check one of the examples of whole pixel difference and particular pixel difference. Here we go. So in whole pixel difference, it gets the coordinate. And basically it says if these 2 pixels, it gets it out of the 2 image. One of them is a good image and the other is an error. And it says if they are not exactly alike, then add a difference. And this is calculating the percentage of that function of the 2 images. It's basically calculating the percentage difference of the 2 images. And basically it's whole pixel difference, and then it gives you the summation, and then you divide it by the entire pixels out there, which is 718 times 980 right here. So in particular pixel difference is a little bit different. Added this if loop or if function to make it a bit easier on the processor. Basically says if it's not exactly alike, then it's going to have to go through a different check. Otherwise, it can skip that pixel if they are exactly alike. So the sum is pixel difference, and let's look at that function. But since there's 3 parts to a pixel, it divides it by 3 after it decides the sum of each of them. But yeah, we have to check what that pixel difference is because I didn't think it was fair to exclude the entire pixel if it was only a little bit off, and that's why I made particular pixel difference and didn't go with whole pixel difference. So let's look at this pixel difference. So in pixel difference, it sets 1 to be the max and the min, and then it it does a reference based off of the smaller. I guess it does it by the max actually. It does the max, and if it's greater than the halfway point, then the base is max. If it's less than the halfway point, the base is minus the min. Interesting. But basically, it's able to return that percentage. And then you add up the percentages and divide them by 3, and that'll give you the total difference. And so that is the pixel difference, actually. But it's kind of interesting because I couldn't go by just a difference amount. Like if one pixel was r equals 1, or let's say r equals 10, and then the next one was r equals 20. Well, that's a 200% difference by normal amounts. So I had to come up with a method to calculate it based off of what is the maximum possible difference that it can come up with. And that's what I came up with here. And let's go back down since that's done. So after it does all of that, it gets the main difference. This is difficult explaining all this. Pixel array 1. I think this is for pixel mount differencing. But yeah, it calculates the difference there. And so this part, final calculation, is basically turning each decimal into a percentage, so it's easier for display. And this final print is basically telling you just an easy way to look at each of them one after the other, and it allows for easy placement into an Excel sheet. So yeah. All right, so now we're going to check out the comparisons themselves. And right here we have a basic picture 2 and error 1, and picture 2 is kind of the verified sample, and error 1 is it's just an error. So what we want is these other picture verified samples to have a low difference compared to picture 2 and a high difference compared to error 1. That's kind of what we're basing it off of. And so in this table, we came up with a delta, and I just minus that, the difference between the error and the sample to try and pick out which one's the best. And I wanted to stick with RGB because I didn't want to do too much processing per pixel. And so out of this one, I actually picked particular pixel because it made the most sense. And pixel amount, while it shows a good result, it does not really account for location of pixels. So one pixel on the top of an image could be the same as the pixel on the other image's bottom. And it's not going to be such a great way to look at quality control. And I wanted something based off of location, as I got the pictures in a very exact spot. So I like to stick with particular pixel and see how that turns out. So I came up with 3 algorithms. The first one is total pixel, the second one is whole pixel difference, and the third one is particular pixel difference. So in total pixel difference, instead of taking account the location of a pixel and its composition, instead it uses the RGB coordinate instead of the location coordinate and putting that location on an array and incrementing it. So it really doesn't take into account the location of the pixel. It's basically just a pixel composition. And then you take, one picture and then minus the other, absolute value it, divided by picture height times picture width, which is basically the total pixels in a picture, and multiply that by 100, and that should give you your percentage pixel difference by composition. So here we have particular pixel difference algorithm. And so really there's 2 cases. Basically this is calculated by a maximum reference of difference, because it's not fair to say that pixel R is 10 and then pixel 2 is 20. So it wouldn't be fair to say that pixel 2 is 200% different than pixel 1, or maybe even 100% different, when there's a maximum of 255. So we use that reference to calculate the difference. So in the first case, the lowest value is below the halfway point of 127.5. The max difference reference is 255 in this case. And when it's above 127.5, the halfway point, the max difference reference is 0. And so let's look at case 2 first. You have 200 and 170. So basically the difference between them is 30, but the reference is 170. You take the smallest value and minus it by the reference, which is 0, because that's the maximum difference. So you have 200, and if you go above 200, you have 255, which is only 55 difference. So 200 down to 0, that's 200 difference. So that's clearly the bigger one, and that's why we use that as the reference. We use the maximum possible difference position as the reference. So you have 30 and 170, and then you do a basic division and then multiply by 100, and the difference is 17.65% difference. So then case 2 is the opposite, where the lowest value is below the halfway point, and so you get the regular difference, which is 30, and the reference is going to be taken from the top. So again, 130 to the floor of 0 is 130 difference. So 100 to 0 is 100. And then 100 to 255 is 155. So the maximum difference, or 100%, is all the way at 155. So then we calculate that difference, and we get 19.35%. And let's see, calculating the blue pixel, this is just to show that it all depends on the lowest value. And so it doesn't matter if both are in one side above or below the halfway point. It always depends on the position of the lowest pixel value. And so that's what we calculate here. 140 minus 120 is 20, but the max reference, same as the lower case, is going to be 255. 14.81%, and then you take the final difference of that and you add them all together and divide them by 3, because between these 3 pixels, or these 2 pixels, to reach 100%, they'd all have to be 100% different. Otherwise it would be 0 for 0% different. So this is just what made sense to me, because they all have an equal part in the pixels makeup. So you add them together, divide by 3, and average them to make 17.21%. And that is the difference between these 2 pixels using the particular pixel difference method. Alright, so here we have the particular pixel algorithm, and I'm going to show you the basic loop that it works in. And so this is the 1 through 19. Let's just explain the loops real quick. This goes through these samples, as is in image 2. And then it has another nested loop right here, and this is specifically for the defects. And basically all it really does is compare the defects in this particular area. So now it does the total. This should probably be outside of the loop, but whatever, it works. And then picture to array. So it sets a sample here, and then picture to array. So it sets that sample to be an array. So now it's much easier to be processed. And so this part's kind of hard to explain. It does something special the first sample that you process. And so you have to make an array or an average out of 2 samples. And then you continually add to that average array, which is what this is. And then it does it again where it says added picture to average for first time, and then added picture to average over and over again. And let's check out some of these functions to explain it better. So let's look at particular pixel difference 3 by array, and that should really take it off. Here it is. So right here it takes the 2 samples and it assigns them to a variable, and in that variable you can access it through the indexes. or in dices, as they say. So you have 0, 1, and 2, and that's what's going to be in it is a tuple of 3 variables, and they represent RGB. And so for particular pixel difference, before we even process it, we just check if it's not exactly the same. Because if it is, it'll just skip over and it makes the process a little bit faster. And so now we have here pixel difference, so it's another function that we got to look at. Here it is. So you see pixel difference, and it assigns the max and min value, and then it makes the difference from that. And then it says if max is greater than the halfway point, then base equals max, and then if it's less than, then it's the highest value minus minimum. Actually, that should probably be max. And then if it equals, but usually that's not the case, but I put it in there because you'll get an error after averaging it so much, and you will hit that halfway point of 0.5, where normally they are just integers. And yeah, that's pretty much it. This part really highlights that you can't examine a pixel the same way you would any other number, where if you have 5 and 10, what's the percentage difference? And you might say it's 200%, because 10 is double of 5. And I didn't want to do that. I needed to examine it through a way that the maximum possible difference would be represented as 100%. And so this is what I came up with. So as you can see here on the left and right, I put the error 1 and error 2. These are the cards that do not have defects on them. They're just different cards. They're actually way out of range with the 29 and 35. And here we have, the control and the 2 defects. And I don't know what happened here, where basically the control sample is going up and down. It doesn't really matter because the results aren't they don't really show much improvement. In fact, they show that 19.1 is improving and that 18.1 is disproving, but it just didn't really make much sense to keep this method, so I had to come up with a different method. The whole pixel concept is pretty basic. Basically, two pixels are going to be considered different if they are not exactly the same, and they're considered similar if they are exactly the same. Now, as we see here, the errors seem to go up as the algorithm is optimized, but the control sample goes up as well, and it shouldn't. So this is why it kind of makes me think whole pixel difference algorithm isn't such a good choice. So now that we've tested all 3 of these algorithms and see that they don't really work the way that we want them to, I decided to come up with filter paths, an algorithm that takes in all the mistakes of the previous ones and hopefully will provide better results. So with the filter paths, to explain it, I have 4 samples in the example, and the first 2 are actually used to create the filter key. So in the beginning, you're going to have 2 pixels in one location, and it's going to create a high and a low pass key. And it's just whichever has the higher number gets the higher number. So a pixel can actually have a high and a low value during the creation. And any verified samples that come in, if the limits, if the pixels are outside of the limits, it will adjust to meet those pixels, and it will basically be adjusted for all future samples that are verified. And hopefully it doesn't matter, because when the defects come through, it doesn't matter how many samples come through. If you have a black spot and all the verified samples are different shades of white, it's not really going to get through, and this helps to widen the gate for verified samples, as there are small, not defects, but small, niches and tendencies in each sample. If any future values are within the filter, usually they're acceptable, otherwise it's considered rejected. So here we have the filter pass array, or the filter pass algorithm. So first we're going to set up the arrays. That's what we do here. Set 20.jpg to an image, and then picture to array, turns the image object into the array where it puts its pixels. And so right here we have image 2 and 3. You have to make the filter, or the key, you have to start off with 2 pictures, not just 1, because you're going to set upper and lower limits. And so I think this part right here was just for troubleshooting, but you don't need that. You can just comment that out. So creating the filter basis right here. And really this just goes through what's high and low. Really the filter high picks the highest value out of both of these, and then the low picks the lowest value out of both of these. But when you start off with 2, one's going to be higher, one's going to be lower, basically. So we'll continue, prints that it factored it in, and then the total image size, all that. And this part is the same as the rest of it, rest of the algorithms, where it factors 1 in, and then it checks the difference between it and 20, and then it checks also with the defects. So let's check the results of that. And right here we have it, filter pass comparison. You'll see the errors go down a little bit because they're more accepting of things, but you'll see that 18.1 and 19.1 actually begin to raise higher than 20.jpg right at this little part, and they actually intersect right here. So yeah. Okay, so now we're going to talk about picture comparison. In which case, we have basically we have algorithm display a picture, and what I wanted was to have the pictures side by side, and anything that would be considered different would be white, and anything that's the same would be considered black. So I wanted this thing to show basically a difference and kind of localize defects. So let's go through what each thing does. Right here, it's a little array creation. You have the filter array low and high. And see difference array, combined picture array. You'll notice that this one's a lot larger. It has double the width of the normal picture that we're using. Text file to array. This was like really difficult to figure out, to bring back text files and put them in arrays. And That's exactly what it does. It's basically pulling from memory for a file. And so let's go up and check that out. Text file to array. Let's see. Read the file. This pulls out a text file for y in the range and x in the range, blah, blah, blah. Let's see, it's going to read a line, and then it's going to take the new line out of it. So a new line is basically when you put a space or when you press enter and it goes to the next line. That's what they call a new line, and it's represented by something called the new line character, which is, you know, slash n, and I needed to take that out. So because it has to be put into an array. And here's the big part. It's putting it into the array, but before it does that, it does ast.literal underscore eval. And basically when it pulls it from the text file, it's a tuple, but the tuple is a string. So I needed to find a way to take out this tuple that was trapped in a string format, and this is the way to do it. And luckily they already had a method to do it because I was about to make one. It'd probably suck. And so here's where the comparison is. We only did defect 2 for this example, but captures it in the image, picture to array, close the image, define image. Oh, okay. It opens it again, picture to array. Now this is the same thing, but, and then it's going to detect filter pass, blah, blah, blah. It does have a filter pass end results. Okay, there it is. Let's see what that is. Because it's supposed to do something where it does the white and black filter pass end results. It appears that it doesn't really adjust anything. This is just giving back a percentage difference. This should be a, oh, it's defect picture array. So let's look at where we could find that, the creation of that. Filter pass end results. Come on, where is it? Has to do something about it. Let's see, define image, comparison picture input. This is all very interesting. But you know what? I don't even think it does that. Wait, yes it does. This is where it combines them. But it has to do it somewhere. Filter pass difference array. Here it is. Finally. So it creates the difference array here. It's not the defect picture array. Okay, so you have the filter array high and low, and then the normal picture, and the difference array is going to be the 1 and 0 inputs where it shows the likeness and difference altogether. And then in this section, it combines them side by side to be in one picture. This is the last part. This is probably one of the worst parts of it, was you can't make an image out of an array until you convert it back to one-dimensional, what they call a sequence, but really it's just one by one. So it makes all this combined array lineup, and then combined picture array, and I made this little equation to figure it out, where it'll step to the next line. But it has to do 2D to 1D, so you have to work with an equation to, I don't know, basically it'll combine it. I guess it's like line by line, but you have to come up with a function to handle both variables for the index. And then it creates this, and then image put data, and you just put in the array name, and it'll do it. Print image, image save. So it looks like that image is called test.png. Let's look at what that is. Should be here. And it's not. Well, I think there's some of them around here somewhere. Let's do 19.1 versus optimized. And here it is. So you can see right here on the original picture, I basically burned it right here. And you can kind of see the burn did extend, but it's not that clear in the color part, but on the white part it is. And you'll see that it is, white for dislike. This is all difference, or considered to be difference. And yeah, so now you can have a graphical display actually different and not just get a number out of it. So here what we have is basically the graphical display of likeness and differences with the defects and the control. The white spots are considered different and the black spots are considered similar, so they're ignored. I made this part as an idea to hopefully show easily the defects in a picture. And so on the right we have control here. And there's nothing really major there. And in 18.1 we have that small dot, and that's really the only defect, but a lot of chunks kind of came out of it for some reason. And in 19.1 the burn is actually clearly shown, and it's very interesting because the white part is very obvious that it's burned, but the color part is not. But examining it and comparing it to other pictures in an optimized algorithm shows that it's actually very different. Now let's go back to the dot here for a second, because basically I tried to calculate the max difference of the 18.1 dot, and so I got on a small scale and did 14 pixels by 17 pixels, and it's basically a circle. So then I have both of those to make the radius, and then multiplied it by pi, got 187 pixels, and that amounts to about a 0.02%, when really the algorithm isn't optimized all the way, and it should take at least 100 samples to keep this optimization clear, and that would be a good start, but really I only had 20 samples to go off of. So here we're going to talk about saving and loading from a text file. And so here we have the saving part of it, a text file. No, this is the saving part. It's going to go through and open a file and write to it, and the range, it's going to pick out the range number from the array and add a new line character so that it's spaced out, and that's going to write to that file, and that's going to close the file after the loop. Text file from array is similar. What you do is you read from file and it goes through the same loop. Hopefully you should just set these ranges to be the same, and then our strip is going to take away the new line character, and array ast.literal eval it's going to take tuple that is a string, and it's going to take the string out and convert it back to a tuple, which is kind of hard to do on your own. So luckily, we have that function to work with. And so I guess it's important to note that when you put it in a string, or when you put things into a text file, it converts them into strings. So this is what a text file looks like. It's basically a bunch of lines of tuples. In this case, this 000 is RGB, all equals 0. When you add the new line character in, it adds this space in between all of them. And so that's why the new line character is in it. So to recap this whole video, for some pointers, it's best to have some precise positioning, consistent lighting, verified samples, defect samples, and using those verified samples for your continually improving algorithm. So here we're going to talk about GitHub and why GitHub is an awesome website. Because what you can do is you can upload your files like so, and it's kind of like Google Drive, except you can update it from your code and commit the changes from your code, which is so yeah, that's pretty much the end of the video. I hope that this has helped you in the future developing your own automated quality control inspection. Thanks.